Hello, in this video we are going to not only finish the antiderivative portion of this module, we're going to finish the module in itself. So here we go. This is about initial value problems, and the idea is when you have a derivative you're working on, or an antiderivative you're working on, and instead of having the plus c, if you have some initial conditions, you could plug that in to your antiderivative and then find out what c would be, and then be able to express it for the particular case and not the general case. So the learning outcomes use antidifferentiation to solve simple initial value problems. Okay, so let's see here. Initial value case is when we have an initial x value given to us and gives the initial y value. We can plug things in. So here's our first example. dy dx equals sine x and y of 0 equals 5. So that means we're going to say when x equals 0, y equals 5. We can plug that in to get what the c would be. So in this case, it might be easiest well, I'll just rewrite this. This notation can be a little confusing for people. This just means the derivative of y is sine x, which means then y would have been the integral of sine x dx. And as we talked about in the last section, that is negative cosine of x plus c. Well, we also have an initial condition. It says that if x is 0, y is 5. So we could say y at 0 is going to be negative, move this over here, cosine of 0 plus c, and that should equal 5. So let's see here. Negative cosine of 0. So cosine of 0 is 1. So that's negative 1 plus c equals 5. So if I add a 1 to both sides, c equals 6. And then we have that our y is negative cosine of x plus 6. And that's it. Let's try another one. So here we have dy dx equals negative 3x squared, and y of 1 is 2. So I'm going to rewrite this as y equals the integral of 3x to the negative 2. So I apologize if I said that wrong. Dx, and that's going to be 3x to the negative 1 over negative 1 plus some c. So we have negative 3 over x plus c, and that's our y. Now we have an initial condition where when x is 1, y is 2. So we can say 2 equals negative 3 over 1 plus c. So I'm going to do it up here now. 2 equals negative 3 plus c, so we add 3 to both sides. We have 5 equals c. So y equals negative 3 over x plus 5. Trying to clean up that 5. Just rewrite the whole thing. There. Okay, we're going to go on to another one here. This one didn't print out, so I'll write it out. We have f of t, this lowercase f of t, equals 8 secant squared t minus 10t cubed, and the initial condition they give us is f of 0 equals 0. So our capital F of x, or f of t in this case, is the integral of 8 secant squared t minus 10t cubed, that quantity, dx. So the antiderivative of a secant squared is a tangent. So this becomes 8 tangent t minus 10, this is t to the 4th. We add one other power, divided by the new power, plus some c. And the initial condition is f of 0 is 0. So that is to say 0 equals 8 tangent of 0 minus 10 over 4 reduces to be 5 halves, 0 to the 4th, plus c. So that implies that c is just 0. And we can conclude that our f of t is 8 tangent t minus 5 halves. Fix that, 5 halves t to the 4th. That's it. Okay, your version of this problem may count a little bit different, but that's the process for it. Okay, let's go on. Decelerating car is another example here. This is an applied problem. It says a car is traveling at a rate of 88 feet per second and 60 miles per hour. When the brakes are applied, the car begins decelerating at a constant rate of 15 feet per second squared. Okay, so this means that I need more space to work, so I'm going to come over here. Our acceleration is going to be negative 15 feet per second squared, if you want that, which is equal to our velocity, v, or derivative of velocity, v prime of t. So our v of t, the antiderivative, is going to be the integral of negative 15 dt, which is negative 15t plus some constant c. Now we're given that we have an initial velocity of 88 before the brakes are applied. So our velocity at time 0 is negative 15t plus c, which equals 88. I should say 15 times 0 because t is 0 here. So that means c must be 88. And we have velocity of time t at time t equals negative 15t plus 88. And the question is, how many seconds elapse before the car stops? So we want to know when the velocity is going to be 0. So negative 15 times t plus 88 needs to be 0. So 88 equals 15t, and divided by 15, t must be 88 over 15. I didn't get the decimal. Seconds. Okay, part B to this says how far does a car travel in that time? So we have to think about the relationship of position and velocity, and that the position derivative of the position function is the velocity function. So negative 15t plus 88. So that means the position function is the integral of negative 15t plus 88 dt. So that's going to be negative 15t squared over 2 plus 88t plus some constant c. And for this, our initial position is 0, so this is a little bit trivial, but 0 equals negative 15t squared over 2 plus 88t plus c. And I keep forgetting, I got to make those t's 0. 15 0 squared, 88 times 0 plus c. So c must be 0. Now we're looking at our position function being negative 15 over 2 t squared plus 88t. And we want to know how far it travels in 88 over 15 seconds. So it's negative 15 over 2 times 88 over 15 seconds squared plus 88 times 88 over 15. Sorry if I'm getting another out right now of the screen. And this works out to be 258.133 feet. Okay. Could be a little bit involved. Let's do one more example here. Suppose the car is traveling at a rate of 44 feet per second, so that's going slower. And it says how long does it take the car to stop and how far will the car travel. So there are a lot of similarities of this problem as the last one. We have our acceleration at time t is -15, which is our derivative of our velocity. And so as we did before, velocity is going to be the integral of -15 dt to give us -15t plus c. In this one, our initial velocity is 44, so that 44 equals -15 times 0 plus c, so that 44 equals c. So our velocity at time t is -15t plus 44. Now if we're trying to find how long it takes to stop, -15t plus 44 equals 0, so -15t equals -44. T equals -44 over -15, or 44 divided by 15. Literally half as much time as the last problem. Now we know that s prime of t is equal to velocity time t, which is equal to integral of, well, it's equal to, that's our -15t plus 44, so that our position function at time t is the integral of -15t plus 44 dt, and that is going to be -15t squared over 2 plus 44t plus c. And again, our position function s of 0 equals 0, so that c would be 0. And s of t is -15 halves t squared plus 44t. So how far does it travel in those 44 over 15 seconds? That's almost 3 seconds. S of 44 over 15 equals -15 halves times 44 over 15 squared plus 44 times 44 over 15. And we get down here 64.5 feet. It'll travel a lot less distance. Okay, well, I hope that you enjoy this section. And then next we're going to jump into chapter 5. Yay.